Okay, hi Year 11. Today we're going to be having a look at 10F, which are the sum and the products of the roots. Again, it's relating back to a polynomial. We've been looking in the last few lessons at polynomials, and we've been looking at what the roots or what the factors of a polynomial would look like. And we would sometimes have a quotient, we would have a divisor, and we would have a remainder. In this section where we're looking at the sum and the products of these roots, we are looking at those roots being the factors, when we write them as factors of our polynomial, and so there are going to be zero remainders in this section. We're going to be having a look at, first of all, quadratics to start with. We'll then have a look at cubics and quartics, and we'll do those three separately, and you'll see the link between the three of them. So we're going to assume that these two symbols here, they're called alpha and beta, so Greek alphabet letters. We need to know that. We're going to let alpha and beta be the roots of this quadratic equation. And what we can do is we can work out by working through these. And if I was to make this quadratic here harmonic and I divided it through by a, what it would look like would be this. Okay. So I'm going to think of this quadratic as being harmonic, and if alpha and beta are my roots, how I could write that as the factors of the, as a product of its factors, are x minus that root alpha and x minus the root beta. If I then expanded that product, I'd end up with this quadratic here. What I then could do would be to think of what's actually happening is, this was the quadratic I gave you to start with. This is what I've got now in terms of the roots. They're going to be the same, so I could actually then equate coefficients. And what I would have that out the front of the x squared, they're the same, so that doesn't help us. That's my a out the front of the x squared. Out the front of the x, I've got b over a. And b over a is going to be equal to minus alpha plus beta. And c over a is going to be equal to alpha beta. When I equate them, we come up with these rules that I've got down here in blue that we need to know. So we've got that alpha plus beta, so the sum of those two roots of our polynomial, is equal to minus b over a, and the product of my two roots is equal to c over a. Now, the a, the b, and the c are always going to be the numbers or the coefficients of our terms in our polynomial. So a is always going to be out the front of x squared, b is out the front of x, and c is the constant term. Just like when we use the quadratic formula to factorize, we'll have our a and b and c in the same spot. So the sum of our roots are minus b on a, the product of our roots for a quadratic are c over a. We need to be familiar with that, and we're going to use that. So let's have a look at how we might use that below. Okay, so example number 1 here talks about alpha and beta being the roots of this quadratic. 2x squared minus 6x plus 1 is 0. And we want to find these 4 combinations in terms of alpha and beta. But the only thing we know is that the sum of the roots is minus b on a, and the product of the roots is c on a. So we can work out these first two fairly quickly. And we need to come up with a formula for C and D that incorporates alpha plus beta and alpha beta. So we'll need to be doing a little bit of rearranging and some thinking with some algebraic manipulations. So here's our quadratic. A is going to be 2, B is going to be minus 6, and C is going to be 1, because that's the way we always have our coefficients of our quadratics. So let's have a look at the first one. Let's have a look at what it's going to be for alpha plus beta. Now, alpha plus beta, the sum of the roots, we've got a formula straight out for that. That's minus b over a. So we can write that straight in. Minus b over a. We're going to have minus 6, because it's minus, and we've got minus 6 all over a is 2. So our answer is going to be 6 on 2, which is 3. So the sum of the roots is 3. That one's fairly straightforward. The second one. Alpha beta, we have a formula for that. We have c over a. So alpha beta is c over a, which is going to be 1 over 2. So the product of our roots would be equal to a half. Let's look at our next one. Alpha squared plus beta squared. Now, we don't have a formula for alpha squared plus beta squared yet, do we? all we know is we've got alpha plus beta and we've got alpha beta. So we need to come up with something that has an alpha squared plus beta squared in it. And I'm going to give you the tip. We're going to have a look at alpha plus beta all squared and see what that's equal to. Now, let's expand alpha plus beta squared because we know alpha plus beta. So squaring that, we know we're going to get some extra terms. So let's see what we get. When we square it, we square the first term. Our second term is twice the first times the second. So 2 alpha beta and beta squared. So this is what alpha plus beta squared is. It's this part on the right-hand side. Now, if you have a look at that, what we've actually got is we want an alpha squared plus beta squared, and this side has an alpha squared plus a beta squared. So if I was to rearrange this equation, so I was left with only alpha squared plus beta squared on the right-hand side, and I took 2 alpha beta away and took 2 alpha beta away, we have something that we can work with. So let's do that. So the left-hand side is alpha plus beta squared minus 2 alpha beta. And my right-hand side is now alpha squared plus beta squared. This is what we want to find. Okay, and I'll do that in yellow again for us. And the other side of the equation has information that we can work with. We now have an alpha plus beta all squared. We have an answer for alpha plus beta. We just need to square it. And we have an alpha beta. And now we have an answer for that. We just want to times it and subtract them. So that is what I mean when I say we need to do some algebraic manipulation when we're looking at the roots in order for us to come up with something that is workable. So our solutions then is going to be that alpha squared plus beta squared is going to be equal to alpha plus beta all squared. Alpha plus beta is 3, so it's going to be 9 squared. Take away 2 lots of alpha beta. 2 lots of alpha beta is a half. So take away 2 lots of a half. 9 squared is 81. Take away 2 lots of a half is 1. So our answer is 80. A little bit of manipulation, but we got there. Likewise, let's look at D. We don't have anything at this point that is going to help us for D. We don't have a 1 over alpha or a 1 over beta, but we need to work with it and see what we can do to make something into some workable roots. What I'm going to do is pop both of these over alpha beta. So what I'm then going to have on the top line is beta plus alpha, or alpha plus beta. We have that. We know that alpha plus beta from our first part was 3. So that is going to be our top line. And our bottom line is alpha beta, which is a half. 3 divided by a half is equal to 6. So we could then use that information to find what alpha and beta are. It hasn't asked us to, but you could also find alpha and beta using a quadratic formula or factorising from our Year 11 work as well. So that would be another familiar way to do it. Okay, let's go down a little bit further down here. Now, second example. It's saying find k if alpha is equal to minus 2 and we have the quadratic kx squared minus 7x plus k plus 1 is 0. Okay, so as soon as you start seeing quadratics, cubics, quartics, and you have a root given to you, we've got some more work to do to find the other one. So what do we know? We know that A is k, we know that B is minus 7, and we know that C, in this case, is k plus 1. That's our constant term at the end because it doesn't have an x in there. We also know that one of our roots is alpha, okay, and we need to find beta. We don't actually want to find beta, we want to find k. And we're going to use our rules for alpha and beta to help us find that. So let's think of what we know. We know that alpha plus beta is going to be equal to minus b on a. So alpha plus beta is minus 7 on k. So 7 on k. And we also know that alpha beta is equal to, remember what that one is? C on A. That's equal to k plus 1 on k. Now there are two equations, but there's something we also know. We also know what alpha is. We know that alpha is equal to minus 2. So from our first one, I could write that minus 2 plus beta is equal to 7 over k. And for my second one, I know that alpha beta, which is minus 2 beta, is equal to k plus 1 over k. So I have two simultaneous equations that I can work with now, 3 and 4. So I need to do something with those. So if you want to pause the video and have a go and see what you're going to do, I am going to rearrange 3 to become beta is equal to 7 over k. I'm going to add 2 to both sides. So beta is 7 over k plus 2. And I'm now going to sub into number 4 equation, my beta. So into 4, I'm going to have minus 2 lots of 7 over k plus 2 is going to be equal to k plus 1 over k. And now we're going to neaten that up a little bit. So let's expand this side here. We're going to have minus 14 over k minus 4 is equal to k plus 1 over k. Make that look more like a k there. Okay, so we have not gotten too far here, but we are down to one variable. So we can neaten this up quite a bit. Now have a think about what you would do here. I'm looking at that and thinking, I don't like that k on the bottom line, so I'm going to multiply everything by k. So that it's going to make it become minus 14 minus 4k is equal to k plus 1. A heck of a lot nicer than with our k's on the bottom. You just need to make sure that when you're multiplying everything by k, you're also multiplying that minus 4 by it. Let's gather like terms. Let's get the k's onto the right-hand side. If I add 4k, I'm going to end up with 5k on the right-hand side, and my left-hand side is going to be minus 14, and I'm going to be taking 1 and taking 1 away, so I'm going to be minus 15. So k is going to be equal to minus 15 divided by 5, which is minus 3. That's the answer. That's what it wanted us to work out, but we could also find our other root, but it only wants us to find k in that case. So you need to be fairly confident with your algebra. I think getting up to, possibly up to here is fairly straightforward, but we're in Extension 1 class now, so we need to be able to manipulate our work and work fairly well with simultaneous equations. So if you're a little bit rusty on those, you may need to go and practice a little bit more. Okay, let's move on down. The next bit, let's have a look at the next example. It says find the value of p if one root of this quadratic is double the other. Okay, so there's a couple of things at play here. It's telling us about the roots. So as soon as you see the fact that we're looking at roots, you know we're looking at polynomials. So when you're thinking of polynomials, you're thinking of divisors, quotients, remainders. And in this case, because it's a root, we're going to have no remainder, and we want to be thinking about alphas and betas. We know it's a quadratic. We know there's two roots. We know the coefficients are A is 1, B is 2, and C is minus 5p. We also need to think, what do we know about our roots when we're talking about quadratics? We know that we have the sum of the roots and the product of the roots. We know that by definition. So we know that the sum of the roots are minus b on a, which is equal to minus 2 on 1. I'm just going to leave it as minus 2. And we know that the product of our roots are c over a, which is minus 5p over 1. We're just going to leave as minus 5p. But we've also been given the other bit of information in our question that says that one root is double the other. So one root, we'll say alpha, is twice beta. So there are 3 bits of information that we know. We need to be able to come up with a value for p. So let's see what we can do with it. Okay, so there's a few ways to proceed. If you want to pause and see if you can come up with a value for p, that would be great. Your way might be slightly different to mine, but as I said, there's a couple of different variations that you could do on this one. I'm going to get a value from 1, and I'm going to say that alpha is equal to minus 2 minus beta. So I've just rearranged that. That's my 4th equation, and I might sub that into 3. I'll say we'll sub 4 into number 3. So then we're going to have that alpha is minus 2 minus beta. So minus 2 minus beta is equal to 2 beta. Does that help us in any way? Oh, not sure yet. Let's have a look and see what we end up with. So we're going to have minus 2 is equal to 2 beta plus a beta, which is 3 beta. We're going to get minus 2/3 is beta. Let's just keep going and see what we end up with. Let's see if we can find what alpha is going to be. So alpha is 2 beta. I have beta is minus 2/3. So alpha is 2 lots of minus 2/3, which is minus 4/3. Has that helped us yet? Let's have a look. We'll just underline what we've got so far. We also know that into 2, I've got that alpha beta, or from 2, I've got that alpha beta is minus 5p. So if I was then to multiply my alpha and beta together down here, I would have minus 5p. So let's do that. Alpha beta is equal to minus 4/3 times minus 2/3, which is equal to minus 5p. So minus 4/3 times minus 2/3 is 8/9 is equal to 5p. So now if I divide by minus 5, I'm going to get p. So 8 divided by minus 45 we're going to have on the bottom is equal to p. Okay, so a little bit messy, but still definitely workable. Okay, before we go on, something I just wanted to just mention in here is with our quadratics, with the fact that we're finding the sum of the roots being minus b over 2, or minus b over a, very similar to our vertex. So let's just draw a quick sketch. If we had a quadratic, and that's not necessarily the quadratic up there, and these are our 2 roots, when we're going alpha plus beta and we're summing those, we're getting minus b over a. If I was to then halve that value, I'd get my vertex in the center of those, which is my formula, minus b over 2a. So that does make sense when you think of that like that as well. And I might make a little note there for us that the vertex is minus b over 2a. And we can see how that differs on drawing a quadratic as well. Okay, let's move down a little bit further. We now want to have a look at cubics. This is the next extension on from quadratics. So I am not going to derive the formula here. We've got it here to have a look at. But what we're saying is if I have a cubic equation that looks like this, ax cubed plus bx squared plus cx plus d, note a is still the coefficient of x cubed, or the leading coefficient. B belongs to x squared here, c belongs to x, and d is the constant term. So just note the difference between the cubic and the quadratic. But instead of having 2 roots with a cubic, we have 3 roots. So I've got alpha and beta, and this third one is called gamma. So just note those. And what we have is a slight variation on our rules. So we've got the sum of the roots, which before was alpha plus beta, but because we've got 3 roots here, the sum of the roots of a cubic is alpha plus beta plus gamma. That's still b over a. Okay, and what I want to think of it as, or what I like to call it, is sum by 1. So I'm summing my roots 1 at a time. Because the second one is a slight variation. When we had our 2 roots for our quadratics, we just had alpha, beta, gamma. Okay, but here we're going to be summing our roots by 2. So we're having every combination summed together. So alpha, beta, beta, gamma, gamma, alpha. So sum by 2, that's c over a. That's the second one here. Before that was our alpha and our beta. So we were still summing by 2 for our quadratics. Here we just happen to be summing by 2 and we've got 3 terms in there. The third one, we're multiplying the 3. But a lot of people like to call it sum by 3. So it's not sum by 3 necessarily because we're not summing. So I'm just going to say by 3. In this case, that's our product of the 3 of them. And that's going to be minus d on a. Now what you'll notice is we've got b on a, c on a, d on a, minus, positive, minus. So if I had another set of roots down here, so, and this is what we're going to have for the next one, for our quartic or a power of 4, I'm going to have minus B on A, C on A, minus D on A, E on A. So there is a pattern there, and the pattern could continue on for infinitely many degreed polynomials. Now, this part here we need to know, but what you would likely be very happy with is this sits in our HSC formula sheet. So here's our HSC formula sheet here. So under the functions, underneath our quadratic formula, we're given a cubic equation with our A, B, C, and D in, and it's giving us those three. So it doesn't give us the quadratic roots, it doesn't give us the quartics or any other degreed combination, but it lets us know that the sum of the roots, the three roots of this cubic, is minus B on A. By 2's, it's C on A, and by 3's, it's minus D on A. So we're given that, which is nice to know to prompt your memory, but you'll probably find that these stay with you in your mind anyway. Okay, so let's have a look if we can use those. So yes, we need to be familiar with these three, and it relates to our cubic. So let's go down and have a look at your first example. Now these very similar to the quadratic, is we're given combinations of roots, and we're going to have to use a little bit of algebra and a little bit of cleverness sometimes to work out what our answers are. So here we're going to have A is 3. B is nothing because we're skipping the squared term. We're missing that. C is minus 6 and D is 1. So don't fall for putting C and B the other way around. That will confuse a lot of people. Okay, so part A, we're looking for the sum by ones. Alpha plus beta plus gamma. The sum of the three roots is minus B on A. Okay, straight up to the top. Minus B, it's 0 on 3. So the sum of the roots together is going to be 0. Let's look at B. The product, or the sum by 3. So alpha, beta, gamma is minus D on A. D is 1, so it's minus 1 on 3. So it's minus a third. Okay, those two are very straightforward. This one, however, is not. We don't have a formula for alpha, beta, beta, gamma, gamma, alpha. Oh, yeah, we do. Sorry, I was thinking of a more harder one. We do have one. It's a C over A. Thinking of the next question. So that's nice and simple. So sum 2 at a time. Just double check that it is the one that we think it is. And that's going to be minus 6 on 3, which is minus 2. Hopefully there's a more tricky one down a little bit below. I'm sure I popped one of those in. Ah, there it is. I knew we had some more. This is the one I was just talking about. We don't have a formula for this. Well, we kind of do. We've got an alpha plus beta plus gamma, and it's squared. So we're just going to pop in our values for alpha plus beta plus gamma, which we have up here, which is 0, becomes 0 squared, which is 0. So that one's, again, fairly straightforward. E, however, we definitely don't have something for this. So please don't go 1 over 0 in this case, because that is not what this is. We need to think of this as an algebraic fraction, and we want to pop these over a common denominator, which is going to be alpha plus beta plus gamma. Okay, so how many times does alpha go into alpha, beta, gamma? It's beta, gamma. Beta goes in alpha, gamma times, and gamma goes in alpha, beta times. That's what we have when we factorize this. It turns into this one below it. So back to your early year 11 work from advanced. Okay, so the top line is our roots 2 by 2, which is up here, which is minus 2. Our bottom line are the product of our roots here, which we have as minus a third. Oops. Okay, minus 2 divided by minus 30 is going to be minus 2 times by minus 3 over 1, which is equal to 6. Okay. Lucky last is F. Now, F again is a little bit trickier. We don't have any combination of roots that we can work with for this one, so we need to expand it. To expand this, expand the first two brackets first. Okay, we'll say expand these first. And then what we get when we have expanded those two, we can then expand, multiply that by gamma plus 1. So if we were to expand the first two brackets, I'm going to have alpha beta plus alpha plus beta plus 1. So you're just basically foiling that first bracket. So alpha times beta, alpha times 1, 1 times beta, 1 times 1. I'm going to times that by gamma plus 1. And now we're going to FOIL that one. If you prefer to have it the other way around, pop the y plus 1 out the front, that's okay. I'm going to times everything by y first. So I'm going to have alpha, or not y, gamma, sorry, alpha, beta, gamma. I might make that a little bit curly so we don't get it confused. Alpha gamma plus beta gamma plus 1 times all of those. Plus alpha beta plus gamma plus beta plus 1. Okay, what have we got? Okay, we have got the roots multiplied together. So we've got this one. We're going to add to that our alpha gamma plus beta gamma plus alpha beta. So then we've got our roots 2 by 2. Got rid of those ones. And then we've got our roots one at a time. Alpha plus beta plus gamma. And then we're going to add 1 to it at the end. Okay, so alpha beta gamma we've got as minus a third. The roots summed 2 at a time is equal to minus 2. Our roots as individuals up here is 0. And then we're adding a 1 at the end there. Okay, so what we end up with is minus a third minus 2, which is minus 2 and a third. And then we're going to add another 1, so we're back to minus 1 and 1/3. Okay, let's move on to the next example. Now, I'm going to get you to change this next example because it is too complex and going to take way too long, I believe, for a HSC exam. Maybe this would be okay for a take-home assessment, but I'm going to get us to change each of those to a squared. Not that we can't do the cubed, I just sat down and did it, and it just takes us too long. I might pop it in the OneNote instead. So HSC-wise, it's just going to be a question that they're not going to do without giving us some steps leading into it. So we've got this quadratic. It has the roots alpha, beta, gamma, and we're going to find what alpha squared, beta squared, plus gamma squared is. So we know that A is 2, we know that B is 0, C is 5, and D is 1. We know that the sum of the roots 1 at a time, alpha plus beta plus gamma, is minus B on A, which is going to be 0. We know that the sum of the roots 2 at a time is going to be C on A, which is going to be 5 on 2. And we know that the roots 3 at a time is going to be minus D on A, which is going to be minus a half. So we know that from what we've just looked at previously. We don't have a rule for alpha squared, beta squared, gamma squared. We need to come up with one. Things are squared, so I'm going to go and take them as alpha plus beta plus gamma. And I'm going to square all of that and see what we come up with. When I square all of that, it's basically saying I'm going to go alpha plus beta plus gamma multiplied by alpha plus beta plus gamma. We're basically foiling it, but we've got 3 terms. So you've got to think about what we were doing when we were expanding. What that means is I'm timesing alpha by the second bracket. I'm then timesing beta by the second bracket. And I'm then timesing gamma by the second bracket. That will give me the expansion of all of this. And I'm going to do that now and see what we end up with. So we're going to end up with as alpha squared alpha beta, alpha gamma, plus alpha beta, beta squared, beta gamma, plus alpha gamma, beta gamma, gamma squared. Let's collect that and neaten it up. We're going to have an alpha squared, a beta squared, and a gamma squared. And we're going to have in there as well, we should have 2 alpha betas. Yep. We're going to have 2 lots of alpha gammas and 2 lots of beta gammas. So what we've actually got now is we've got that alpha plus beta plus gamma all squared is equal to alpha squared plus beta squared plus gamma squared plus 2 lots of alpha beta, beta gamma, gamma alpha. Now, what we are wanting to find in this question is we've been asked to find alpha squared, beta squared plus gamma squared, which is this part in here. So if I was just to rearrange my equation, I've got my solution there. And I now know that alpha squared plus beta squared plus gamma squared is equal to the sum of the roots, all squared, take away 2 lots of the roots 2 at a time, which I can work with. So the sum of the roots, alpha plus beta plus gamma, we've got a value of over here, that's 0. Oops, let's fix that page up. So that is 0, so I'll pop in a 0 for that over here. 0 squared 0 minus 2 lots of the sum of the roots 2 at a time. So the sum of the roots 2 at a time was equal to 5 over 2. So we've got minus 2 lots of 5 over 2. So our answer is going to be minus 5. And that's our solution for a squared plus b squared plus y squared. Now, this is a very long video, guys, so you may need to pause and have a little break. We're still going, and we've still got a fairly long way to go. Find the cubic equation whose roots are twice those of this polynomial here. So the roots of our polynomial here are going to be alpha, beta, and gamma. But our new equation is going to have roots that are twice of those. So our new equation, or our new cubic, is going to have roots that are the size of 2 alpha, 2 beta, and 2 gamma. Okay, so this one's a little bit harder. Had me thinking for half a second there. So it says when we're finding the cubic equation whose roots are twice of these, our new cubic is going to have these roots here, okay? 2 alpha, 2 beta, 2 gamma. But for this original polynomial, we know these 3 things here, okay? We know that our 3 roots are alpha, beta, gamma. We know that the sum of our roots, 1 at a time, is minus b on a, which is going to be 3 over 2. We know that our sum of our roots 2 at a time is c on a, which is 0. And our sum of our roots, our roots 3 at a time is minus d on a, which is minus a half. So we know that. But we need to think, well, finding the new cubic equation. If these over here are our roots of our new cubic equation, then our new cubic equation is going to look like this one here. Okay, x minus 2 alpha, x minus 2 beta, x minus 2 gamma. That's our new cubic. So what I did was I just expanded that out, okay? I expanded those first 2 terms to get this one here. And I still needed to times that by my second bracket. And I ended up with the line that's got some highlighted parts in there. Okay, I've ended up with this line here because I've expanded x by all of those terms and then minus 2 by all of those terms. So I want you to pause it and have a go and make sure you end up with this line I've got here. And I've gathered like terms and ended up with this one here. So I've ended up with x cubed plus minus 2x, which I'm going to make that as just a minus 2x, so we don't need that plus in there. So x cubed minus 2x squared. I've got the sum of the roots 1 at a time, plus 4x, the sum of the roots 2 at a time, minus 8 times the sum of the roots 3 at a time. So just by neatening up the line before, I've managed to pick that up nice and easily. So my new quadratic is going to be x cubed minus 2x squared times the sum of my roots 1 at a time, which is 3 over 2, plus 4x, the sum of my roots 2 at a time, which is nothing, so that term disappears, minus 8 times the sum of my roots 3 at a time, which is minus a half. Let's just tidy that up once and for all, and we're going to end up with x cubed minus 3x squared. This term disappears altogether, and I'm going to have at the end plus 4 equals 0, and that's my equation. Okay, the video is either going to keep going, or maybe what I'll do is I might pause this video here, upload it, and then make a second video for this lot of work, which looks at quartic equations. Let's just do it that way. and I'll see you in the next video.